Good morning, everyone. I am Alessandra Soro, Community Manager of VSPARTICLE and Material Pioneers. Today, we will have a webinar about the origins of structure, insensitivity, and heterogeneous catalysis with Dr. Charlotte Vogt, Principal Investigator at Technion Institute of Technology in Israel. I would like to give you a very short introduction about VSPARTICLE and our technology. So VSPARTICLE was founded in 2014 as a spin-off company from the TU Delft University of Technology, located in the Netherlands. With over 20 years of experience in the synthesis of aerosol and with the help of a passionate young team of scientists and engineers, VSPARTICLE is helping leaders and companies reducing the development of new materials and products. We do this by developing and commercializing a whole new technology to automate nanoparticle production. And we are key nanotechnology providers in different industries, such as catalysis, semicon, and health. At VSPARTICLE, we are committed to speed up the development of new materials by improving nanoparticle research, by providing products enabling the production of nanostructured materials for fundamental and applied research, based on simple to operate and scalable principle. We are always happy to provide you with additional information. About today's webinar, please feel free to share your questions about the presentation in the chat, and we will collect them by the end of the webinar. If your question won't be answered, no worries. We will send you a reply via email in the upcoming days. We can now start with the webinar on the origins of structure insensitivity in heterogeneous catalysis, presented by Dr. Charlotte Vogt, Principal Investigator at Technion Institute of Technology in Israel. Please, Charlotte, you can now share your presentation and the floor is yours.
Thank you very much, Alessandra. I hope that you can now see my screen. Alessandra?
Yes, Charlotte, your screen is visible.
Perfect. Okay, so first of all, thanks very much for inviting me to discuss a recent publication from a lot of collaborators, a lot of contributing parties. This work we recently published in Nature Communications a couple of months ago. It's a collaborative effort by Utrecht University, Stony Brook, Oak Ridge National Lab, Technion Institute, BASF, and it was funded by the Dutch Organization for Scientific Research. Since then, I've moved to the Technion, where I've started my own lab. So that's a little bit about the people behind the presentation itself. So I want to talk today about a very fundamental concept of catalysis, something that's been empirically observed for decades, but really didn't have a good rational explanation, in my head at least, for a while. So to begin, structure sensitivity is like I said, an empirically observed phenomenon. We have about 3 classes of structure sensitivity that we observe, or insensitivity. The first and most well-known maybe is an example is the Fischer-Tropsch reaction, where the bond cleavage of CO, pi bonds, is the rate determining step. And the type of structure sensitivity that you see is that the smaller a nanoparticle goes, the less of the types of sites are available to cleave those pi bonds, and thus you see less activity. And that's actually the way that we define structure sensitivity. Does the turnover frequency, the surface normalized activity, does that change with catalyst particle size? So pi bond structure sensitivity we have observed. We also know that there is sigma bond structure sensitivity, for example, in steam methane reforming, where the cleavage of a sigma bond of the CH bond of methane is the rate determining step, generally speaking. And there we actually see that those bonds are preferentially cleaved for smaller nanoparticle sizes, preferentially over a highly under-coordinated site. So the smaller you go, the better the activity becomes, the surface normalized activity becomes. And then we have this other class of structure sensitivity, structure insensitivity, where basically the activity of a catalyst does not change with catalyst particle size, which is an interesting phenomenon. Examples of that reaction are examples of that type of structure sensitivity are, for example, adsorbed alkyls on the recombination of an adsorbed alkyl on the surface of a metal, is an important step in ethene hydrogenation. So a little bit about why that exists. Why do we see that phenomenon? And of course, we want in supported metal catalysts, we want to make as much use out of the often most expensive part of a catalyst that we have, which is the metal. So we want to make smaller and smaller nanoparticles, generally speaking. This allows more surface to be exposed relative to the bulk. And while doing that, while indeed creating more surface exposed for smaller nanoparticles, we also see a different ratio of sites for different catalyst particle sizes. So actually the types of surface sites that are exposed for different nanoparticle sizes changes. For a 5.5 nanometer particle, for example, you have a lot of this pink, which is bulk, basically, non-surface atoms. And of the surface that is exposed, a lot of it is highly coordinated or blue, terrasites, etc. For a very small nanoparticle, that changes. So a lot less bulk, and of the surface that is exposed, most of it is under-coordinated. So that explains that for those two different types of structure sensitivity, we see that different behavior. Different molecules like to be cleaved by different sites. And we extensively studied these reactions, these types of concepts or these types of reactions over the last couple of years. And we used a set of silica-supported nickel nanoparticles. These were created by deposition precipitation in a range of about 1 nanometer to about 6 nanometers. And this was quite an effort to synthesize these. This is especially for transition metals, it can be quite difficult to synthesize, especially small nanoparticle sizes. So we were very happy that we were able to obtain that. We fully characterized those, of course, with all kinds of different laboratory techniques, high resolution STEM, hydrogen chem absorption, etc., to make sure that really the only thing changing in that set of samples was the particle size. And we studied different kinds of structure sensitive reactions. Here we show the structure sensitivity of CO2 hydrogenation. We show that it changes with catalyst particle size. So that means it's a structure sensitive reaction. The turnover frequency, surface normalized activity has a maximum at about 3 nanometers. So that was nice. We were able to use those catalyst nanoparticles to show that CO2 hydrogenation is a structure sensitive reaction. And then we did extensive studies, operando spectroscopic studies to explain why. There are two main reasons from theory actually that already stemmed. One is that there's a geometric effect, basically the different types of architectures, nanoscale architectures of those different sites. And the other one is an electronic effect. Once you go smaller and smaller in nanoparticle size, you start to feel, for example, the effect of a support much more strongly. And even below about 2.7 nanometers for nickel nanoparticles, you start to get things like quantum effects. Atoms or nanoparticles start behaving more atom-like, less metal-like, more defined band structure. Or not band structure, more defined energy levels actually. So we were able to see with quick X-ray absorption spectroscopy, which you can see here on the left, we were able to pulse back and forth between CO2 and hydrogen, and see that the ratio of metallic nickel changed during the reaction. So it was ever so slightly oxidized the surface and reduced. And we were able to observe two different speeds of things that were happening during one pulse, which means that there has to be two different speeds of two different types of things that can go on a surface within one pulse. So this is the geometric effect mainly, and smaller nanoparticle sizes always oxidize a lot more. And this is the electronic effect mainly. So structure sensitivity we understand. We understand why it's there. There are two main contributing factors: geometry, electronics. And if we then start to think about structure insensitive reactions, and we take the same information, we take the same basic understanding that we have of these structure sensitive reactions, in fact, it's quite interesting to know that these reactions are empirically observed at all, because these structure sensitive effects, they're dependent on, as I said, on the electronic effect and on the geometric effect, and these can be correlated based on Bundstedt-Evans-Polanyi. But of course, if you have a catalyst and you change, for example, the type of metal, you're affecting the electronics of the catalyst. You're going to have different catalytic behavior. And if you have a nanoparticle, even though, for example, the active site should be a top site, and those top sites, adsorbate on the top site of a metal, those top sites change for different catalyst particle sizes. The energetics of those top sites change. So it's actually, in fact, very, very interesting that that was empirically observed. So we went ahead and we tested again. We took our catalytic nanoparticles. We actually synthesized even more and tested in CO2 hydrogenation. We indeed saw still this structure sensitive effect. And we tested also ethene hydrogenation, which was a classic example, often studied in literature, of a structure insensitive reaction. And we see that the order of magnitude span, let's say, that that this catalyst undergoes is much, much smaller. So we do, in fact, empirically observe structure insensitivity. So we wanted to investigate this in much more detail. We took different approaches. The first approach that I want to discuss is our in situ high resolution transmission electron microscopy investigation. And for that, we used model catalysts. For this, we had to look at nanoparticles. We wanted to study them in gaseous atmosphere, and we wanted to look at what was going on with the catalyst nanoparticles, exactly what the structure of the catalyst nanoparticles under reaction conditions. So what did we do? We took a prototype's MEMS reactor and a holder. We went to Oak Ridge National Laboratory, and we prepared samples on those silicon nitride membranes, on those silicon nitride MEMS reactors, using the spark ablation nanoparticle generator, the G1. And we used for this the diffusion accessory, because these silicon nitride windows are very, 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 very brittle. And if you're using, for example, size selection with the spark ablation nanoparticle generator, we have the problem still of breaking these. But of course, you get high resolution with in situ TEM, so we can focus even on different nanoparticle sizes using this diffusion accessory. And using diffusion means that you're going to get all of the different nanoparticle sizes within the aerosol that you create from sparking. So here we are. We loaded this silicon nitride membrane cell into our prototypes holder, and as you can see, we were able to take larger scale images. We saw that there were some larger nanoparticles, some smaller nanoparticles, and we can really zoom in onto these onto whichever particle size basically that we wanted to zoom into. So what we did, we started with a reduction. This was a very important step, actually. If we did, of course, many different experiments, and we observed that if we didn't reduce before we turned on the beam, the electron beam, we would get a lot of carbon deposition. But if we reduced our sample in the hydrogen atmosphere, keeping it at 500 degrees Celsius for at least an hour, and then we started to measure, in this case at 150 degrees, but also at 400 degrees, we would see no carbon deposition. So this was a really great way for us to study this reaction, even though there were, of course, gaseous reactants involved. We were still able to get a really nice, clear image of the nickel nanoparticles. So again, we took our catalysts to the reaction temperature that was interesting. For the ethene experiments, that was 150 degrees. For the carbon dioxide experiments, which we also did, that was 400 degrees. And we flew, in the beginning, we just purged with nitrogen, and we flew the reactant. And after we flowed the reactant, we flew hydrogen. And every single time that we did this, every single nanoparticle that we checked out, we always saw an expansion of our facet. We did a fast Fourier transform. We always saw that these lattice grains expanded by about 2%. And once they contracted, it was a little bit of a bigger standard deviation across the different nanoparticles that we measured, but it was about 2 to 4% contraction again after we flowed hydrogen. So again, different areas here. You can see a different nanoparticle that we measured. We really were able to obtain very nice lattice structure, and this is really because we used this this approach. So we had our MEMS reactor, of course, and directly onto that silicon nitride membrane, we deposited these nanoparticles, and this allowed us to get basically lattice fringes, and basically to be able to see this expansion. Because if there's a support in the way, an amorphous support in the way, you'll have problems focusing this well and getting the microscope aligned in such a way that you can actually see for a lot of different nanoparticles consistently the lattice fringes. So this was a really great way to measure that. So, okay, we observed this lattice expansion. Then we wanted to know in more detail, in more chemical detail, and later on also in more electronic detail, what happened to these nanoparticles. So now we're moving back to supportive nanoparticles, so nickel on silica, and we checked again CO2 hydrogenation versus ethene hydrogenation here in IR spectroscopy. So with IR spectroscopy, of course, you probe vibrational frequencies, and that means that often you're able to observe reaction intermediates on the surface of supported metal catalysts. So we're here checking what's on the surface, what's causing any different activity that we observed a couple of slides before. So here we see different nanoparticle sizes, small, medium, and large, increasing nanoparticle size, same here, small, medium, large. For the CO2 hydrogenation experiments, for the structure sensitive reaction, activity changing for different nanoparticle sizes, we saw different reaction intermediates in IR. We saw, depending on the particle size, different peaks. And this was something that we'd already observed before. This was something that we used to explain the structure sensitivity effect in a previous publication. And now we took this structure insensitive one and see that for the different nanoparticle sizes, we see no change. We see no change in the observed reaction intermediates on the surface. And we were able to, if we change, for example, the reaction conditions of the ethene hydrogenation reaction, we were able to obtain different peaks. So if we change, for example, the partial pressure of hydrogen versus ethene, we did see a different reaction intermediates on the surface, like we would expect to see. So nothing really crazy here, right? This is structure insensitive, no activity change for different nanoparticle sizes, structure sensitive, okay. Then we move to X-ray absorption spectroscopy, which is a really good way to probe structural changes in our catalyst nanoparticle. Local geometric changes around the average absorbing atom, around the average nickel atom, let's say. Not just that, we can also observe oxidation state changes, of course, more in the Zanes region, more in the beginning part of these spectra. But basically, if you're going farther and farther away, if you're looking at these wiggles at higher and higher energy, you're starting to look at the effects of local geometry. And again, comparing ethene hydrogenation to carbon dioxide hydrogenation, structure sensitive reaction, structure insensitive reaction, and there we saw something counterintuitive. Now we see that actually the structure of this structure insensitive reaction, the structure of the catalyst, is changing much more significantly for the structure insensitive reaction than it is for the structure sensitive reaction. We see that the wiggles going from green to blue, going from reduced to reaction, are very significantly changing. This indicates quite a big local restructuring. And again, for the structure sensitive reaction, we only saw a little bit of oxidation basically in the beginning of the spectrum in the Zanes. In fact, X-ray absorption spectroscopy is quantitative, can be quantitative, and we were able to quantify the surface normalized restructuring that we observed using that technique. So we took two different spots. We took the white line, most indicative of the oxidation state, I would say, for nickel, and we took a point a little bit farther on, which is starting to go towards geometry. And we compared the change that we saw going from reduced to reaction for, in this case, CO2 hydrogenation, in the next slide for ethene hydrogenation, and compared that change for the different nanoparticle sizes. And there we saw that actually the surface changes, the surface normalized absorption changes. So for different nanoparticle sizes, of course, you have different amounts of surface, but this is normalized for that. You see that the smallest nanoparticle, or the medium nanoparticle size, that it restructures the most. We see actually, in fact, that our surface is restructuring, actually correlated to the activity of that reaction. So CO2 hydrogenation had this nice maximum at about 2-3 nanometers, and that's also where we see the most restructuring. For the ethene hydrogenation sample, first of all, these are on the same scale, these plots. Now you see that there's much more restructuring, again, as we already saw just empirically, or just qualitatively, let's say, but there's also particle size dependent restructuring. Smaller nanoparticles restructured less. Again, this is surface normalized, and larger nanoparticles restructured much more. And this is strange, that there's particle size dependent, surface normalized restructuring for that structure insensitive reaction, completely counterintuitive. So let's take a closer look at what can be causing that restructuring. If we take a Fourier transform of this left part of these spectra, we obtain more or less a radial distribution function of the average absorbing atom. So at about 2 angstroms, we can see the first nickel neighbor of the average absorbing atom. At 4 angstroms, we can see the nickel-nickel neighbor, the next nearest neighbor, multiple scattering pathways. This is a measure for order in the nanoparticle. If you see something here, let's say if you see a peak at about 4 angstroms, that means that there is local order. And if you don't see it, that means that there's local disorder. And funnily enough, we see local ordering and disordering going from reduced to reaction. And with that ordering and disordering, we see this peak coming up, this nickel-carbon bond. Could only be nickel-carbon in this case because there's no oxygen in this reaction environment. So there's nickel-carbon that's attaching to the nanoparticle, and it's creating a disorder in the nanoparticle. So here we see about 70,000 of those spectra plotted with time on screen, going from 0 to an hour about, and we pulsed back and forth ethene and hydrogen, ethene and hydrogen, ethene and hydrogen, and CO2 and hydrogen, etc., etc. Here we see no real significant changes for our CO2 catalyst again, but we do see ordering and disordering, actually reversibly so for the ethene pulsed experiment. If we take those 70,000 spectra and we fit all of them using FEFIT for the Debye-Lala factor, and again, for this experiment, all other things being equal, that can be a measure for the amount of relative surface restructuring, and we take the derivative of that Debye-Lala factor, we plot that against time, then we're able to obtain information about the reaction kinetics, or about the restructuring kinetics of the nanoparticles in these different pulses. So 4.4 nanometer particle that we measured restructures much faster than the smaller ones. The reversibility of the restructuring actually decreases with particle size. You see the first peak is always the highest, but for the smallest nanoparticle size, after that first peak, it's quite difficult to distinguish others afterwards. So there's always a degree of restructuring that's irreversible because this first peak is most intense. So these are quite some interesting observations, and especially the fact that larger nanoparticles restructure faster, we were able to couple with the observations that we had in our in situ high-resolution transmission electron microscopy because we observed grain boundaries on the larger nanoparticles. And in fact, carbon dissipates into grain boundaries approximately an order of magnitude faster than it does for clear surfaces. So coming back to this structure sensitivity, structure insensitivity question, if there is this thing which apparently restructures the surface so significantly, restructures the surface of nanoparticles so significantly, that might be the thing that is causing a certain amount of surface to be exposed. This is a hypothesis that was already proposed by Sommerjai somewhere in the 80s, along with a couple of other hypotheses, because he also thought that it's quite strange that surface structure insensitivity exists, where if it is the case that something absorbs irreversibly onto the surface, and irrespective of the previously exposed surface, only exposes a certain amount of, or certain type, of sites, then yeah, irrespective of the nanoparticle size, there will always be the same, or nominally the same surface sites. So we took that hypothesis and we wanted to test that both with activity and with spectroscopy. So we took different sizes of nickel nanoparticles. We flowed ethene over the surface, restructured the surface, and then cleaned it. So first purged nitrogen and purged hydrogen, which means that only this irreversible amount of restructuring should still be there. And then we did a structure sensitive reaction. We measured the activity of CO2 hydrogenation before and after restructuring. Before, we see a clear difference in the turnover frequency, and after this structure sensitive reaction, by cause of that restructuring due to the ethene, is now structure insensitive. It is still active. We did still see CO peaks absorbed onto the surface, but those were very specific CO peaks that we saw. So it does indicate indeed that there was only a certain type of site that was still exposed. So to sum up, basically what we've discussed here today and what we discussed in the article, structure sensitive reactions have quite a clear dependence on sites, have quite a clear and clearly described dependence on the different types of sites that are available versus the different types of reactions and reaction intermediates that are there. Structure insensitivity also has that same type of dependence. However, at least for this specific structure insensitive reaction, ethene hydrogenation, the recombination of an alkyl with a hydrogen being the rate determining step, this empirically observed structure insensitivity is most likely in fact caused by the surface being the same of the different nanoparticle sizes, which changes our fundamental understanding of this concept. In fact, we proposed those reactions to be termed apparently structure insensitive rather than truly structure insensitive. And of course, this work was made possible by a lot of people, which I would really like to thank. Bert Weckhuizen, my former PhD supervisor, Anne Todi at Stony Brook, Ray and Marta at Oak Ridge and PSI, and all of the collaborators and funding agencies that have contributed to this work. And I would gladly take any questions if there are.
Thank you so much, Charlotte, for your presentation. We actually have 2 questions lined up. I'm going to read them for you. Yeah, so the first one is, how was the in situ TEM samples pre-treated prior to their exposure to the ethylene gas mixture? What are the condition boundaries of the in situ TEM chips?
So if I'm not mistaken, those chips, they have a pretty good heating, like you're able to heat them up pretty good, up to I think about 800 degrees. We used 500 degrees because we know for our nickel nanoparticles that that is enough to reduce them fully, and we kept it there for 1 or 2 hours, I forget. But yeah, so we reduced them in hydrogen, and actually, as I tried to mention before, if we did not do that and measured electron microscopy images before we fully reduced our nanoparticles, we would really have a lot of annoyance from carbon deposition. So the carbon itself, the carbon contamination itself surrounding the nanoparticles, or still in the cell, or maybe even in the microscope. Yeah, those would deposit. So this was a very important step, to not turn on the microscope before we finished reducing.
Thank you. We have another question, so I'm going to go ahead and read it. During your in situ TEM measurements, did you also observe the lattice expansion contraction phenomenon for other particles? For example, particle of different sizes?
Yeah, so we focused actually on the nanoparticles that were about 5 nanometers, because we didn't want to, so we recorded the most images of those nanoparticles because they had very clear lattice fringes to start out with. But yeah, there was always, to a more or to a greater or lesser extent, there was always a degree of restructuring. But yeah, later on it made sense, of course, that this was particle size dependent, and that we saw for the smaller ones, we first of all weren't able to see as many lattice fringes, but if we did, then we saw actually a smaller expansion.
Thank you so much again, Charlotte. So I would like to encourage everybody that has questions to just post them in the chat, so we can make sure Charlotte can pick them up. We will wait for a minute or two to just make sure everybody can post their questions, and then we will end the webinar. We have another question. Do you have strategies to limit carbon deposition in the ETEM?
Good question. So ours was all empirical, and what I've noticed is that the most important thing is to reduce the flow, to have a reductive atmosphere, non-carbonaceous reductive atmosphere. So we used hydrogen and we heated it up, and we just kept it there for a significant amount of time. Even if we measured at lower temperatures, like at room temperature images before reducing, afterwards we would see still some carbon deposition. It wasn't as bad as that we would measure while we were reducing. Let's say we would record electron microscopy images while we were reducing. But if it's at all possible to have to heat up the sample, and even have some vacuum there, for example, then that should do the trick. And just not to measure before you heated it up. This was our little trick.
I'm going to go ahead with another question. Did you explore catalyst on other supports? Can you speculate on whether the structure insensitivity is translatable to other supports, for example, titanium?
So we explored in great detail. We explored structure sensitivity on different supports. We have nickel on all kinds of different supports of different reducibility, which showed us that the activation energy of CO2 hydrogenation doesn't actually change for the different supports, but the activity really does, which means that the most contributing factor, let's say, there is whatever is caught in the prefactor of the Arrhenius equation, being the geometry of the active sites, most likely. And so taking that, let's say what we know for structure insensitivity, or what we hypothesize for structure insensitivity, it would yield the same results. It would yield that if geometry is that, the most determining factor here for the change in activity, then I would expect them to change to the same extent over those types of supports. Of course, once suboxide species start coming into play, this could be a way, actually, if you, for example, reduce your titania partially and you have some creeping of suboxide species onto the nanoparticle, then of course you're blocking certain sites, which may affect the degree of restructuring that can occur, but of course also the activity. So would be interesting to play around with reducibility of supports and trying to see if we can make actually ethene hydrogenation a truly structure sensitive reaction. That would be interesting to do. Yeah. Wow, I see a question from Andreas. That's a really nice question. Should I read it out?
Please feel free. Yeah, please feel free to go ahead yourself. Yeah.
Awesome. So can I conclude that in a structure insensitive case, the smaller the better is the rule for an efficient catalyst? Where's the limit to this rule? So I wouldn't go as far as to say the smaller the better. That's one thing, because I've really seen that even for reactions like that are typical sigma bond reactions, sigma bond activation rate limiting reactions like methane activation. So I have to switch to my other speakers because I hear them. Still hear me?
Yes, we can hear you.
Perfect. I'm sorry. Because even for those types of reactions, for those that are really textbook, sigma bond type structure sensitivity, you see that if you go to much smaller particle sizes, you don't see that exponential effect that you're supposed to see, or that people have reported. Actually, it goes down again once you go to smaller nanoparticle sizes. Why? Because a real catalytic reaction is, of course, a cascade of different steps. So once you optimize to the fullest extent a given, let's say, rate determining step, if you take then it can very well be that another elementary reaction step becomes rate limiting. And this is the case in many cases. So I would say that for ethene hydrogenation, yeah, probably also a particle size of around 2 nanometers would be a good catalyst particle size, because of course you have a lot of surface area exposed, etc. But then you can also you need to also take into account that these, generally speaking, agglomerate faster, of course. So it's very dependent on, of course, on reaction conditions that you want to apply, etc., etc. But at least now we know the playing field. At least now we know that that it shouldn't actually matter too much, the particle size, indeed. Yeah. And then I see another question here. How do you determine particle size distributions of supported nickel particles with STM? The contrast for small particles and support seemed quite low in the micrographs shown at the beginning of the presentation. Let me just share this again. I clicked that away. I wouldn't argue that the contrast is too low here to determine particle size. Although these are dark field images, and we have also bright field images of these catalysts where it was quite easy to see the nickel nanoparticles, and we took a lot of images. So this was quite an extensive study to really look at the nanoparticle size. Of course, you can also determine them with Xray absorption spectroscopy, which is also what we did. We looked at the coordination numbers. We looked at the hydrogen chemabsorption profiles. We checked from all different angles we used. We checked the nanoparticle sizes, basically. And then another question. So you've demonstrated the particle restructuring for nickel-based catalysts. Do we expect the same for other heavier metals, for example, heavier metals? Short answer, yes. I was talking about the work from Sommerjai in the 80s, where he saw also surface restructuring on single crystal facets. And this is where this sort of trench formation of ethylidyne intermediates in ethene hydrogenation comes from where a given topside is exposed irrespective of the previously exposed surface. And this was seen on ruthenium. Ruthenium surfaces, I think he did it also on palladium. So these seem to be pretty universal type of conclusions, I would say, looking at the other literature that's already also out there, especially surface science studies.
So I guess we still have a couple more minutes for a question if somebody has any, or if there is something Charlotte would like to highlight. We still have a couple more minutes. Otherwise, we can just go ahead and wrap up the whole presentation.
Sounds good.
I think we have the last question.
You mentioned 1,000 seconds, sorry, the XF spectra were obtained. How long does it take, and how do you analyze so many? Good question. So thousands, sorry. You mentioned thousands of XF spectra. So yeah, we measured at 100 millisecond time resolution, and we did binning of the spectra until they were of sufficient quality for us to do our XF analyses on. So how long does it take? I would imagine you mean the time resolution of the measurement. So that's actually at the X10DA, at the Swiss light source. Excellent beamline where they have really fast and high quality spectra that you can measure. And how do you analyze so many? This was a challenge. This was something that Florian Meijer at Utrecht University helped out with. He, or actually facilitated. There's open source code, Fefit code, which you can plug into basically any language that you want to analyze your data with. So what we did was we took those 70,000 spectra and we processed them in MATLAB, and we ran Fefit code on all of those. So it was a really nice challenge to fit all of those correctly. We took two outliers, so let's say the reduced catalyst, and then the most catalyst with the most change during reaction, let's say, and we fit those separately in Athena before we determined our fitting strategy, let's say, and then we used those parameters to do a batch fitting with Fefit code in MATLAB. Yeah.
So I would like to thank Dr. Charlotte Vogt for her presentation, and all the VSPARTICLE's team for this webinar. It's been really a collective effort, and I would like to thank everybody. We are always happy to answer your questions and start a conversation with you about potential collaboration. So please feel free to reach out to us via sales@vsparticle.com and visit our website to discover more about VSPARTICLE technology. And I guess we are ready to go. Have a beautiful day, and thank you so much, Charlotte.
Thank you very much. Bye-bye.